Welcome to the Shape of Space Matrices. This lesson is on variations on matrix multiplication. Okay, the first thing we're going to look at here is outer product, and we saw this before. I gave you an example. Here I'm presenting it in a little bit more general form. So we have a n by 1 column vector times a 1 by m row vector. And when you multiply those together, you get an n by m matrix. So the first entry here is V1 times U1, and then you get this entry here is V1 times U2, V1 times UM. Then you proceed to the second row and V2 times U1, V2 times U2, and so on. So that's called outer product, and really the only thing new here is the term. This is just standard matrix multiplication. Then if we shifted the order, if we took the U vector first and then multiplied it times the V vector, you would get the inner product. But in that case, you need to have M and N equal to the same number. And there you just get a scalar. The output is just a scalar. Then down on the bottom here we have let A and B be M by N and N by P matrices. So in other words, you can multiply them because this number of columns in A is equal to the number of rows in B, which is required to multiply two matrices. Then let AI star represent row I of A. So we're kind of starring out the column. So this is just row I of A. And B star J represent column J of B. The product AB is defined to be the M by P matrix C, whose entry IJ is given by this expression here. It's just row I times column J of B, which you could represent as this sum here. You may want to think about that for a few seconds just to convince yourself that's true. That'll show up a lot in subsequent lessons. And this is effectively the inner product of row I of A with column J of B. Consider matrices A and B, where A is M by N and B is N by P. And we want to find column J of the product of A times B. And it's actually this expression here, where these terms, the capital A's here, this is column 1 of matrix A, this is column 2 of matrix A, all the way up to column N. And then these elements here, B1J, B2J, BNJ, are the elements in the jth column of B. Okay, so that's a bit to take in. You might need to think about that a bit to convince yourself. It does come up in a lot of proofs, and you'll see different textbooks just assume that you know this, and it's usually not explained very carefully. So I thought I'd take a little bit of extra time to do that. Let's look at a particular example. So we have A and B here. And let's find the first column of C using this method here. So we want C star 1. So J would be 1 in our equation here. So we'd get B11, B21, B31. And then first one would be the first column of A, second column of A, third column of A. All right, and we plug all that in here. So we have 2, 3, 5, 2, 3, 5, and then the three columns of A, 1, 2, 5, 1, 7, 3. We multiply each one of these out, add them together, and we get 52, 22. Now, what you want to do is double check that. So if we multiply A times B, And in particular, we want to get this, we're only computing the first column here, so let's take first column, the first row of A times the first column of B, and we get 2 plus 15 plus 35. That's 52. Then to get this here, we get 4 plus 3 plus 15, and that's 22. So it does check out. We get the same result by either the standard multiplication that we've talked about many times before, or using this column by column method. This is useful if you only need a particular column. For example, in a computer program, maybe you only need one column at a time based on some result, or in different proofs, it's sometimes convenient to just talk about a column at a time. And so this gives you a way of doing that. I have yet another way of looking at this in the next slide to reinforce the point. We have another example on this slide. In this case, A and B are both 3 by 3, but as we saw, they don't have to be square. They just need to be of the appropriate dimensions to multiply together. And what I want to do here is find the third column two different ways. First way is through multiplication. So we take row 1 of A times column 3 of B, get this. Then row 2 of A times column 3 of B, get this. And then finally the third row of A times the third column of B, and we get this. So that's the normal standard way of multiplying to get the entries in a column, in this case the third column. Then our formula, in this case, as we're looking for the third column, is this here. We're just plugging in the j equals 3 in our formula. And so we get B13 times the first column of A, B23 times the second column of A, and then B33 times the third column of A. And if you multiply and then add, it's pretty easy to see that you're going to get the same as what we have up here. Okay, so yet another way of doing multiplication. And as I say, it comes up in different proofs, so it's good to spend a few minutes convincing yourself that it does work. We have another approach for multiplying matrices together. It does result in the same output as the normal multiplication. This one's called the outer product method. And to multiply A times B with their appropriate size for multiplication, we take column 1 of A times row 1 of B plus column 2 of A times row 2 of B, and so on up to column n of A times row n of B. And this sum gives us the product A times B. We can look at an example using A and B from our example from a few slides back. So we take the columns of A, 1, 2, 5, 1, 7, 3, and then we multiply those times the same numbered row of B. So 2, 1, minus 1, 3, 3, 2, 5, 1, 4. Then we multiply these out. These are basically three outer products. We get these matrices, and then we add them together, and we get this. If you recall, we only computed the first column when we did the previous example, but if you check the other multiplications, you'll see that this is in fact the same as multiplying A times B using the normal method of multiplication. I have an example here of the outer product for matrices, where the matrices are 3 by 3 in this case, and I've color-coded it to help us visualize. So first let's use the outer product method. So we take the first column of A times the first row of B, so that would be A11 times B11, A11 times B21, and so forth, and you get this here. Right? That's just the vector outer product, and then you do the same thing for the second column of A times the second row of B, We get this outer product. Then finally the third column of A times the third row of B. Again, this is another vector outer product, and we get this here. Then if we add these together, I preserve the different colors, and we get this here, and we can just check one of them. For example, let's check this first element here. So we'd have A11 times B11 plus A212 times B21 plus A13 times B31. So that checks out. So using the outer product method for multiplying matrices gives us the same result as using the normal matrix multiplication. I haven't seen this used as often in proofs as the previous method that we talked about using the columns, but and I have yet one more approach that it's even less common, but just to be complete, I'll give you sort of the full picture, the different ways of different variants in multiplying matrices together. You should always get the same result in every case. We have another method here of multiplying matrix A times B, again assuming they're of the appropriate size. In this method, row I of C, the product of A and B, is given by this formula here. So row I of C is gotten by taking a linear combination of all rows of B, so row 1, row 2, up to row n, with the coefficient being the elements of row I of A. So this is AI1, AI2, all the way up to AIN. So I'll give you an example where we compute we'll use our same example from before, but we'll compute it differently. So first we'll do the first row of the product. So we'll put in 1 for I here. So we get A11 times the first row of B, then A12, which is 5, times the second row of B, and then we only have 3 rows and columns, so we have A13 times the third row of B, so A13 is 7. You have that. Then we add those together, first multiply and then add those together. We get this, and then we do the same thing for the second row. In this case, I is 2, so we get A21, which is 2, times the first row B, then A22, which is 1, times the second row B, and then A23, which is 3, times the third row of B. We get this. And so this is our product. If you take, this is the first row and this is the second row, this is the product AB. And if you recall, this is exactly what we got on the previous slide. And in fact, the very first example we did, we only did the first column, but we did get 5222. Okay, so that's 4 different ways really, if you count the standard way of multiplying 2 matrices together. And as I say, sometimes these come up in proofs, and it's useful to know how to do these in different ways. We have another type of matrix multiplication on this slide. This does not result in the same output as the other 3 methods that we talked about, or the standard method for multiplying 2 matrices. This is actually a simpler way of doing the multiplication. It's called the Hadamard product, sometimes element-wise product or Schur product. And just to give you an example, will make the point pretty easily. So you have 2 matrices of the same dimension. Let me point to them. So you have A and B, for example, 2 by 2. And the Hadamard product, you just multiply like entries. So A11 times B11, A12 times B12, and so on. And it's this symbol that represents the Hadamard product. Okay, so that's not the typical way of multiplying matrices, but in some cases it comes up as part of a formula, And it sounds like a really fancy name that might be something complicated, but actually it's the simplest form of multiplying two matrices. Not as useful as the normal way we multiply, but it's something to keep in mind. All right, so that was the last slide in this lesson. I have 3 more lessons in this series on matrices. So stay tuned. If you like this, give it a thumbs up, please, and also consider subscribing to my channel. Thank you.